Okay, so welcome to this stand-up comedy hour about type-safe C++. I am Björn Fahller. I live and work in Stockholm. Something wrong? Okay, so I guess we'll restart it then. Recording running? Okay. So, welcome to this stand-up comedy hour about type-safe C++. I am Björn Fahller. I'm from Stockholm in Sweden, where I work with writing software for networking equipment. I've been doing C++ for roughly forever. I think I wrote my first C++ program in '93. So, shows my age, I guess. Show of hands, who thinks C++ is a type-safe language? Surprising number of hands. Who thinks it's not? One hand. Okay, so yeah. Well, thank you, then I'm done. No, we're going to talk about type-safe C++, and we're going to have a lot of fun. What is type safety? You had opinions about C++ being type safe. You should have an idea of what type safety is. No suggestions? Here's what Wiktionary says. The extent to which a programming language discourages or prevents type errors. The extent, I think, is interesting. So we can have degrees of type safety. We can have poor type safety. We can have mediocre type safety. We can have quite okay type safety. We can have really good type safety. And discourages or prevents is also interesting. How many of you were here on the previous session when Patricia talked about? Patricia was here. Good. About security. I think that since C++ is a language where we can do ugly casts, given that we can take the address of something and do type punning to really weird things, we cannot really prevent against Machiavelli. But we can prevent against honest mistakes to make it at least a little bit difficult to do type errors. And we'll see about that in a while. This is my take on what we mean with a type-safe system. That it's a system that discourages or prevents use of one type when another is intended, or discourages or prevents operations that don't make sense. Patricia mentioned the semantics of types, and specifically the lack of semantics of the fundamental built-in integer types. And also discourages or prevents the use of values outside the defined space. So by that, I sort of sneaked in the introduction of the agenda. So these are the topics I intend to cover. So let's dive into type safety in C++. This is something that started in a rather embarrassing way in my career. I had code like this. I and my team, we were implementing a communications protocol where we send out requests, receive acknowledgements to the requests, and we identify the request with a request ID, so that when we receive an acknowledgement, we can see that, okay, it's that request that was acknowledged. And then we can add and remove receivers to data flows. And can you see the bug on the slide? That was very, very embarrassing. You've never done that, have you? What did you do about it when you had that kind of problem? Facepalm. Facepalm, yeah, that's what you do. You facepalm. I did that. But I also started wondering, apart from fixing it and looking rather embarrassed, I started wondering, can I do something to make sure that this doesn't happen again? So I was wondering, if we have this situation, I have some function other that takes an A, and I have a function that calls other with a B. When is this call allowed? And you cannot really say, can you? Because we don't know anything about A and B. What about this? Is this allowed? Yes, it is allowed. Type safety in C++ is a complete joke. Thank you very much, I'm done. Or am I? What about this? So now A and B are structs. There are, I would argue, the same-ish. I mean, both have exactly one member, the type is int, the name of the member is value. Is this allowed? No, it is not, because A and B are similar. They look the same. They are equivalent for some degree of equivalence, but they are not the same. But if I wanted to compile them, what can I do? Well, I can add a constructor to A that we can construct A from B. Then it works, provided I'm not marking it as explicit. Or I can add a conversion operator from B to A, provided I'm not saying it is explicit. Then I'm allowing the call. Or, of course, I can make it an inheritance hierarchy where B publicly inherits from A, then the call is also allowed. But if I'm not making the choice explicitly to allow it, it isn't allowed. So if I just start like this is the first steps on the rest of the story. Instead of having these type defs for request ID and receiver ID, I make these small structs. And I have this same mistake. Then I get this compilation error. No known conversion from receiver ID to request ID for first argument. This is pretty good. Yeah. So there is a solution. By making sure that my types actually are distinct types, they're not just aliases that pretends to be something different. So we have control. By default, everything is forbidden. We are like medieval rulers. We make the laws as we see fit. And anything we don't like is by default not allowed. We must permit it. So I can write like this instead. I make receiver ID a class that I can construct and convert back to the underlying type. And some comparison operators, because that does make sense. Maybe relational operators. And then I thought, actually, when I wrote an earlier version of this talk back in the winter, I had something like 20 slides on how cool C++17 is with the Enum class that you can use as a safe integer type. Because you can construct an Enum class that doesn't have any enumerators. You can just construct it with any value that fits. And you can get it back with a static cast. And everything else is forbidden, unless you write functions for your type. So that is super cool. But then Olafur's fruit salad happened. Anyone heard about Olafur's fruit salad? There was a discussion on Twitter about how cool this feature is. And in the morning when I woke up, I found this. Olafur posted this link to Matt Godbold's Compiler Explorer, and Pete Bindles responded, did you just slice an orange into an apple? So I had to click on the link, didn't I? So we get this. Enum class orange, enum class apple, create an orange 04, create an apple 3, create an apple from an orange bugger. No compilation warning. This is bad. This is really bad. Shafiq noticed, oh wow, this seems rather undesirable, and points out to which paper seems to be the culprit. Richard Smith agrees, this is really not what we meant. I really like Olafur's response to that. Did I just find a bug in the C++ standard? To the best of my knowledge, this is handled as a core language issue. I have not checked up if it is on the issue list, but I hope it is. So yes, Olafur, it looks like you did. So for now, I cannot endorse using enum class as safe integers. I really wish I could, but currently not. Hopefully soon. Maybe next time I deliver this talk. We'll see. So we're back to this, writing a lot of code. And it feels like a bit of pain, especially since I have to do it again for the request ID, because they are really, they have the same properties. So, of course, I had to wonder, can I do something about this? And there comes the next step. So, what I did next was I started to write a very, very simple, small library at work to make it easy to create your own safe types. So the idea I came up with is this. What I'm presenting here is somewhat simplified, but it conveys the idea. So I have a class template safe type that takes a T. T is the type we wanted to represent, and then a tag type. I'll get back to the tag type in a very short while. So we can create it from a T, and we can convert it back to a T. And to prevent cross constructions, I don't want to, again, repeat Oliver's fruit salad, although this actually preceded that discussion by 5 or 6 years. To make it impossible to create an orange from an apple, I do this. I explicitly delete the constructor that takes another T or another tag. And the tag is actually not used for anything else than to make types distinguished, different. So that if I have one safe type int with one tag and another safe type int and another tag, then they are unique types that have nothing in common, and we cannot cross-construct them. And also you add the same kind of prevention for assignment and whatnot. So this works. So I can now write my type int1 is a safe type int with an int1 tag, int1 underscore tag. And int2 is a safe type int of int2 underscore tag. The interesting thing here is perhaps, if you're not familiar with this, that the tag types are forward declared where they are needed. These tag types aren't used anywhere else in the entire system. No one cares. They're just there to ensure that int1 and int2 are different types, even though both are representing ints. So I could write my code like this instead, say that request ID is a safe type of uint32t and a tag, and receiver ID is also, and note that I have different tags for these, so they are different types. So when I have this bug, again, and compile, I get a fairly decent compilation error message. Safe type blah blah blah, receiver ID tag is not safe type blah blah blah, request ID tag. It's not ideal, but it's really not bad. But then what we can do is something that perhaps looks a little bit surprising if you haven't seen it. We say that request ID is a struct that inherits from safe type of request ID. Have you heard about the CRTP, the curiously recurring template parameter idiom? So who has never heard of it? Okay, there are a few hands. So let's explain this, showing my age again. I read about this first in Jim Copleen's book, Advanced Programming Styles and Idioms, that I bought summer of '93. The thing is this. You saw how safe type handled the tag. It doesn't actually use it at all. It's just there. It's a type. It's used to distinguish it from other safe types. If you read the source code, you struct request ID colon. Now here at colon, request ID is known to be a type. It's only forward declared. We don't know anything about it other than that it exists as a name, meaning that we can pass that name to template. We can have pointers to it. We can have references to it, but we cannot get any other information from it. We cannot query its size. We cannot call member functions because it's not defined yet. But this is enough. Then we can inherit from safe type of an unsigned type and request ID, because safe type's use of request ID is just to know its name. So this is safe. This is perfectly cool. So yeah, request ID is defined in terms of request ID by name. And then I have this, I forgot what it's called now, where this using, where we say that, yeah, and request ID uses the constructor of safe type, so I don't have to repeat them. And with this, I get exactly the compilation error that I want to. It says, candidate function not viable, no known conversion from receiver ID to request ID for first argument. Victory. And I was really happy with this, and honestly, this code is still used at work. Well, not exactly this code, because as I said, this is a simplification, but still, it serves its purpose. It's good. Then to remove or reduce at least the boilerplate, I'm a sinner. I use the preprocessor to repeat things so that my colleagues can write just this. Safe type is a request ID. Safe type request ID is a uint32t. This is not more typing to do than to write a type def, but it provides a lot more safety. This is good. So let's dive into what other people have done. There are a number of libraries for this. I decided to use two examples. I will not go into them in any depth, really, but just to show you a flavor of some things that are available. So this young man, Jonathan Miller, Foo Nathan on various social media, posted this type-safe library. Zero overhead utilities for preventing bugs at compile time. What's not to love, eh? I have the GitHub link there. This is a rather rich library. You can create your types and piece together the behavior that you want your type to have. And it also includes a number of other things that arguably don't really belong there, but they are good, like an improved optional type and the version of stud variant that has some cool extra features. So this was in 2016, so it's not very. It feels like it's been available for so much longer, but it is fairly new. The way you use it is this: in this strong typedef.hpp, you have a class template strong typedef, and you see the ID. You have a tag type and the underlying type, and you can default construct them and copy and move construct, and you can get the underlying values. Everything is const expert, everything is no except, and it's generally cool. And when you use them like this, they are just a handle. You can get a value, and you can store a value, and you can retrieve a value, and that's the only thing you can do. And the way you use it is you include this strong typedef.hpp. Jonathan uses this construction in all his documentation, so I don't feel very bad about the alias. So you use the CRTP to say that my handle is a strong typedef of my handle, and int, you recognize the pattern. But then comes the clever bit. Inside the namespace typesafe, there is a strong typedef op namespace. And in that are operations that you can add to your type. So you say, yeah, and by the way, I want my handle to be equality comparable. Neat. And I want an O-stream insertion operator. So that is pretty clever. It actually completely blew my mind when I saw this originally, because now I just add the operations that I want to my type. So sort of picking Lego pieces and building my type here, like that, without having to do very much work. There's also a more high-level version where you can say that, yeah, and my int, by the way, is an integer arithmetic type. And here comes a surprise. It actually surprised me a lot when I started using these types of strong types in my code, introduced them. I have not found a single use for an integer arithmetic type. Maybe my code base is weird, I don't know, but I haven't. I have found use for something else that a lot of people mistake for being an arithmetic type. I'll get to that in a while. But this is cool. I really strongly suggest you take a look at this library. It's cool. You can, since you define your own types, you can add your own functions to it. Like I said, you retrieve the underlying value with a static cast. But there is also a get function. This get function exists with many overloads that does the right thing for constant volatile and R-value reference and L-value reference. It's neat. And then you have this guy, Jonathan Bokara. Are you reading his blog, Fluent C++? Good. The rest of you're bad people. Start reading. He's excellent. He's absolutely brilliant. He also has such a library called nametype. It's a much smaller library, and it doesn't aim as high. It intends to be simpler. But it allows you to piece together your strong types with your desired behavior. And in addition, it has some conversions for like types. I like the idea of nonlinear conversions, like from watts to decibels and what have you. Watch his Meeting C++ talk. It's absolutely amazing how he introduces, he uses his library as an example of how you can write much more expressive code when you have strong types. So do watch it. The way you use his library is nearly the same. Everything is in the namespace Fluent. And so you say, like, my handle is a Fluent name type, underlying type is int, and a tag. Here comes a different from Jonathan Miller's library, in that the functionality, Jonathan Bokara calls them skills. The skills are part of the template parameter list. So you just add them. And this means you don't have to repeat, like you had in Jonathan Miller's, where you publicly inherit from them and say that, yeah, comparable my handle, printable my handle. Here you just say, yeah, I want it to be comparable, I want it to be printable, I want it to be hashable. You can use the CRTP, of course, if you want to. And here's an odd one. I'm not entirely sure if I think it's a good idea that you can make your types implicitly convertible to something, but I think it is a good idea that if you want them to be implicitly convertible, you have to be very explicit about it. So that part is good. And I'm not going to talk more about these libraries. You can check them out yourself. They're well worth it. Both of them, by the way, are such that if you're reasonably familiar with writing template code, it's easy to add your own functionality, your own skills. It's really not a big effort. So if you want something that isn't covered, add it. It's not difficult. So what happens with your code when you use strong types? Because it actually changes it. Like I mentioned, I work for Net Insight in Stockholm, where we make networking equipment. And one of the things we really pride ourselves with is that we know exactly how much network capacity is used everywhere in the network. And we do this with, it's a little bit odd. I won't go into the details. But we have an idea of a network utilization, a quanta that we call a slot. And we group them together in frames. Frames are typically about 1,000 times bigger than I showed here, but it would make the slides completely incomprehensible. And we identify data flow with slots. So in this case, we can say that we have a green data flow that occupies 8 slots in total. And we group them in ranges, so you can say that it's range 3 through 4, 7 through 8, 13 through 16. And we have the blue data flow that is much smaller, just 3 slots. And we can say that the white is unused network capacity. This ability to express ranges is really important because we do set arithmetics on these, and being able to handle large chunks together saves a lot of computation and memory. So with this, we have types, slot index, and slot count. This is pseudocode, obviously. You cannot forward declare a type by just saying type name and the name of the type. I wish we could, but we can't. But I just wanted to say that slot index is some type. I don't want to go into exactly what it is just yet. And slot count also. And we have slot range that contains an index that is a start and a count that is a length. So if we look at the frame, you can see that the rightmost green range is starting at slot 13, slot index 13, and it has a length of 4 slots. And now let's look at code. Peter Sommerlad gave me a hard time about this example because it's a bad example. He's right about that, but never mind. I have a function where we can query available capacity, and I get 0. I guess as far as magic numbers go, maybe 0 is the one you can get away with. But it's still bad. It doesn't have any semantics. It doesn't mean anything other than the value 0. If we just do this and say that it's a slot count of 0, it's not megabits per second or whatever, it's a slot count. We have conveyed meaning to the code that wasn't there earlier. And also because it's tiresome to write that, so obviously you give it a name. Say, no, slot count of 0, that's no slots. So we have given it a name. So just by doing this alone, we have added some semantics and we have given names to things that makes it easier to reason about the code. This is not the biggest advantage, but it is an advantage. But here comes a big one, encapsulation. We're implementing a binary protocol where we stuff information into binary packets. So we want to serialize them. And we see that slot counts are serialized as 24 bits. And this is really bothersome. This code is repeated, not in a lot of places, 3 or 4 places throughout the code base. But this is something that deteriorates after a while, because for some reason, maybe we decide that 24 bits was not the right size. We should use something else, and I have to look up all places. And it gives the wrong information at the wrong place. I'm not really respecting the what level of abstraction I'm working on. But if slot count is not just a type def for an unsigned integer type, it is actually a type of its own. I can overload functions on it. So I can say, let's introduce this idea that all types of data that we want to put into a message buffer, we always put them into the message buffer via this function serialized data, which is a huge overload set. We write serialized data for request ID and receiver ID also, and a lot of other stuff. And then we say inside that function that, yeah, it's 24 bits we serialize it as. And then we can make it more typically C++y by just adding simple function templates as a member to the message buffer. So I can write buffer.serialize capacity. Now we get the right information at the right level of abstraction. Here, when I'm building the message, the important thing is what data do I stuff into my message. How they are encoded is not really important here. That problem belongs elsewhere, and it's hidden. Well, hidden. It's implemented inside the serialized data function. So just by making sure that this is a type of its own and not an alias, I can overload functions and I gain an advantage when it comes to encapsulation of information in my code. So that is good. And then we have type semantics. One thing that made me really upset was this. I have a slot pool. It has a lot of things, but it caches the number of unused slots. And when I have this function release capacity that takes a vector of slot ranges, I obviously just wanted to loop over them and add the length to my slot count. And this stupid strong type does not allow operator plus equals. Maybe I should have used an arithmetic type. But then I started thinking, or should I? Exactly what operations do I actually want to support here? So I started wondering, do I want to be able to add slot counts? Yeah, well, obviously that was the example that made me a little bit upset. So yeah, I want to add slot counts and get new slot counts. That makes sense. Do I want to be able to subtract slot counts? No, I do. Do I want to be able to multiply them? No. Maybe in some other universe that there is a situation where this makes sense, but in my domain it doesn't. So no, I want to make that forbidden. Do I want to be able to scale it, to multiply it with a ratio, to say that I have this amount of slots and I want 3 times as many? No, why not? And do I then want to divide slot counts? Why not? And get a ratio from it. It makes sense. This slot count is 5 times as large as this slot count. Yeah. And then it comes naturally that I want to be able to scale it down with a ratio also. But the slot indexes then. The slot indexes denotes positions in a frame. Do I want to add them? I see shaking heads. No, I don't. It makes no sense. Do I want to add slot indexes to slot counts? Yeah, I do. So, for example, I can then easily iterate over slot ranges, saying, for example, that if I am on the slot range, the rightmost green one that starts with 13 and its length is 4, that means that the next range starts at 17. Cool, that is good. I like that. Do I want to subtract slot indexes? Yeah, to get slot count. That makes sense. Divide them. Now my synapses begin to hurt a little bit. I don't think I understand what that would mean. So no, I don't. Divide them by slot count. I am developing a headache here. No. Scale them. No. Multiply them. Slot index squared. No. Multiply by slot count. No. Go away. Scale them. No. Do you see a pattern here? Do you recognize this pattern? Have you seen this in code before? An excellent example in the standard library is std_chrono, where on the right-hand side you would have the time points. There are positions, absolute positions in time. And you can subtract 2 time points and get a duration, which is the type on the left. And you can add durations, you can subtract durations, you can scale durations, you can add the durations to a time point to get another time point. Cool. I'm onto something. This has been seen before. When I discovered this, I was sort of looking for a terminology because I saw this pattern in so many places. And this is actually something that my code base is filled of. There's so many examples of this. And this is why I don't have a need for any arithmetic type, because this is what I need. Adi here brought my attention to something that I did not know of. In mathematics, these are known as affine space types. So in mathematics, an affine space is a geometric structure that generalizes the properties of Euclidean spaces in such a way that these are independent of the concepts of distance and measure of angles, keeping only the properties related to parallelism, ratio of lengths for parallel line segments. So if you think about a two-dimensional space, then you have positions on that space, coordinates in a coordinate system, if you like. And you have displacement vectors that is the difference between them. And if vectors are parallel, you can talk about their lengths in relation to each other. And you add vectors, displacements to positions to get new positions, etc., etc. And when you scale this down to one dimension, you get exactly the problem that I described. You get what std_chrono implements or models. I had absolutely no idea about this, but I'm glad I have found a name. So that is cool. Affine space types are everywhere in my system. Yeah. So let's look at test code. Test code is weird. Test code is not like other code. Let's take this example. We have some function throttle capacity. If we decide that we have a number of data flows on a link in a network and we want to squeeze it down a little bit. So I can have this test to see that this is implemented in a fair way. So I have some destination client I create with a capacity of 5 and another with a capacity of 8. I place expectations on them that I get a call back about a reduced capacity when I call this throttle capacity. And this code is so short and so confusing because the throttle capacity to 4 or 5, which is 4 again, which is 5. Reading the prototype at the top, yeah, 4 is a request ID. Yeah, sure, okay, yeah, whatever. This is bad. So, of course, you have learned that do not use magic numbers, give them names. So we create a variable, request ID, that is a request that has a value, and we can use it, and now the code is a little bit clearer. It's not entirely obvious what 5 and 8 and 2 and 3 are. So let's continue on this path and give them names. For the love of everything that is sacred, do not do this. Do not do this to your colleagues or to yourself. This code went from bad to completely unreadable. Don't. Generally speaking, I agree with the idea that you don't use magic numbers. But test code is different. I'm talking now about example-based tests. I think it's better to, in this case, I give them a semantic. I say that node client with capacity slot count 5. Now we know what the unit is we're talking about. But we're also exposing the number, saying that it is 5 and it is 8. And I expect to be notified that the capacity goes to 2 and 3 when I throttle it to 5. 2 plus 3 is 5. Yeah, that makes sense. That part of the test is probably correct. 5 down to 2, 8 down to 3, probably fair scaling. Yeah, I agree. This is a decent test. So in example-based tests, I think it makes sense to use magic numbers, but give them semantics by explicitly saying what type you're talking about. And that is sort of it. You asked a few questions, so I ran out of time. Or rather, I finished early. But what we can conclude is this, that safety for built-in types is abysmal in C. You saw the early example with the C-style enums and floating point values. It doesn't make any sense whatsoever to be able to do that. And narrowing costs and overflows and what have you. But structs and classes are as strong as you wish. You must explicitly add the functionality. If you're not doing that, they just hold values, and that's it. And there are libraries that make this easier. So you don't have to do it from scratch yourself. You're free to, of course, if you want to. Think about your types and the operations, because this improves your understanding of the problem. Like my discovery of these affine space types and their relations. Because by then making my types support only the operations that make sense to do, I'm improving the code, I'm improving my chances of writing the right thing. And beware of the urge for convenience. It's really convenient to have implicit conversions to and from everything, but then you sort of lost the thing you strive for, that is the type safety. And strong types leads to more expressive code. You have fewer magical numbers. You give things names. You get better encapsulation. And you get tests that explicitly express intent. And I think that is good. And be careful with the type def, because it sort of gives the illusion of introducing new types, and it doesn't. It just gives a new name for something. And I'm really surprised you haven't asked the obvious question, so I'm going to assume you have. What's the cost of this? You recognize this construction? A safe type with a tag. I've added some addition and subtraction operations. So we have 3 safe types here, safe integers. And I have a function that really doesn't do a lot. It just calls another function with the sum of two other types. And we can see it here in the compiler explorer, what it compiles to. I would argue that this is not an awful lot of overhead. But it gets more interesting. I have some more complex functions, say func that operates on references and updates each other. So we can see it here. It becomes a move, an add, a sub, and a move. So that seems pretty good. Then I do the same thing with type aliases. You know, by the way, what you call APIs, a derogatory term for APIs that use primitive types, called primitive obsession. Don't do that. Do not fall for the primitive obsession. So we have a primitive function. It does pretty much the same thing as savefunc does. Move, add, move, sub, move. It's one instruction longer. Why is primitive func one instruction longer than the savefunc? Any ideas?
You could have aliasing.
Aliasing, exactly. The aliasing rules of the language says that pointers to distinct types, different types, may not alias to the same object unless they are related, for example, by inheritance, or unless one of the types happen to be a char. So in the case of the primitive func using these aliases t int 1, t int 2, t int 3, they are all int references. So they are all of the same type. So the compiler must assume that it is perfectly possible that all of these three references alias to the same variable. So it must check between operations, did it change? Whereas with the save type, these are distinct different types. They are unrelated. They are not allowed to alias. So the compiler can say, I know that this is not going to change between updates. I don't have to reread and see if something has happened. And if you call these through a reinterpret cast, then you are the bad guy, not the compiler. So don't be afraid to use safe types for fear of runtime overhead performance cost. It's typically free. You can actually get a performance gain. In this example, we have a negative cost abstraction. How cool is that? I admit that I actually had to work a little bit to find an example that showed a direct gain. So don't expect that, but you can get it. But do expect to not lose performance. So with that, I got to an end. I didn't actually intend to beat my drum over my experimental strong type, but since Tony Van Aerd mentioned it in one of his talks at C++ Now a couple of weeks ago, I decided that I might as well. I consider this one to be experimental. Feel free to use it for experiments, absolutely not in production code. Feel free to give me feedback and pull requests. And I do take the liberty to, at any time, change anything, just so you know. And with that, I thank you for your attention. Questions? You're stunned completely. Well, thanks.